Hello, everyone. My name is Heng Wan, and you can call me Alfred. I'm from the Pacific Northwest National Lab. And today, my presentation topic is landscape metrics in Dasymetric mapping of population. I'm sorry that this title is a little bit different from what has been presented on the booklet, because I think our lab has forced us to use the presentation slides template. As you can see, the majority of this content is occupied by the image, so there's only a very limited space for the title, and my original title is very long, so I have to change it. Sorry about that. And so I make lots of maps, but I don't consider myself as a very rigid, real cartography. So that's the reason why the first time I saw this word, Dasymetric, I'm quite baffled. What does that mean? It sounds a very hard word for me as a non-English speaker. But I think for most of you, as a real rigid cartographer, I think maybe you should have a better understanding about the Dasymetric. What does that mean? So if you don't, I will introduce the meaning of Dasymetric later in the next slides. So next, I'm gonna give you some background introduction. So for the population data, so it's an important data input for many research fields, such as demography study, urban planning, and disaster control, and also economics, etc. And in the United States, population data are normally aggregated and the census tract, block group, and block level. So these are administrative levels. But before the year of 1990, population data only at the census tract level. So which is the most coarse resolution among all the three levels. And so this work actually stem from our greater integrated coastal modeling project called ICON, the ICON multi-sector dynamics study. So in that greater project, we are actually researching on the interactions between the human and the environment under the future climate change scenario in the eastern coastal United States. So we are actually using the agent-based modeling to model the population dynamics as well as the housing price dynamics under the future climate change. So this modeling actually requires us to use the population data input and the block group level starting from the year of 1970, which does not exist dating back to that year. So we need to find some efficient and accurate way to downscale the population from the census tract to our desired block group level. So that's the reason why we implement the Dasymetric mapping of population. So after some research, so I found out actually, so here the definition is the Dasymetric mapping of population. Its definition is assign population from the source zone to the target zone based on the ancillary data set. But actually, after I did a bunch of literature review, I found actually the definition is wrong. It's actually not what the original author, the original author of the Dasymetric mapping think of. But there are so many researchers in this population, the demography field, so they wrongly used this definition. So I think right now most of the people would use this wrongly defined definition for this jargon. So I just so I just insisted on this wrong definition. And the next jargon is the intelligent Dasymetric mapping of population. So so this is just based on the Dasymetric mapping of population. So we are actually training a statistical regression model and the source zone, and then we do the predictions and the target zone. And the predictions gonna be used in the Dasymetric mapping of population to assign the population based using the prediction and the weights. And so there's actually a little story I can share with. So while I was preparing my manuscript for this work. So I just wrote, I just like get this jargon, intelligent Dasymetric mapping of population from the literature review. And I just sent the original manuscript to my colleagues, and they were all like surprised about the name, because like they think I am just kind of narcissism people. Why do you call your method intelligent? And I have to explain the name is like originated from the historical literature review. It's not like made by myself. Yeah. And so I would say like the previous population downscaling, the Dasymetric mapping of population, so they ignore the cell level patterning of imperviousness. So they normally just use the ancillary data sets such as imperviousness, road networks, and also nighttime light imagery or land cover information to facilitate the downscaling of population. But they ignore the cell level pattern information. And here I'm going to introduce the landscape metrics. So the landscape metrics are the measurable units of the landscape composition and act as a surrogate for the change, and it can thus allow us to depict and quantify the spatial patterning of the ecological processes on time and on space. And so landscape metrics are normally like mostly used in the ecology study. So people use landscape metrics to study like the fragmentation of the habitat area. And so in our study, so for the population downscaling, so we are deriving the landscape metrics from the imperviousness area, from the urban area, so which we believe it can potentially capturing the urban patterning information, which corresponds to the population distribution. And here, this diagram shows like some of the landscape metrics I have used in this project. So both its definition and some of the example plots for the high value and the low value of each of the landscape metrics. So some of the highlighted landscape metrics, such as the land shape index, number of patches, or the patch densities, as you can see. So different like urban impervious patternings would have like totally different landscape metrics values. And here, so this is the landscape shape index value for the state of Connecticut derived from the imperviousness between 20% and 100%. And so initially observing this image, we can see that actually the low LSI, the low landscape shape index actually corresponds those high population density regions in Connecticut. So this figure just shows some potential of the landscape metrics in depicting the population distribution. And based on our previous literature review, we found that no study to date has examined the predictive power of the landscape metrics in the population downscaling field. That's why we're gonna like research on this topic. And next, I'm gonna talk about the methods. So we have chosen 4 states as our study area, including Connecticut, South Carolina, West Virginia, and New Mexico. So as you can see, so these 4 states representing different population density areas. So as Connecticut has the highest population density, while the New Mexico has the lowest population density. And the right figure shows the flowchart for our intelligent Dasymetric mapping based on the landscape metrics. So scanning from top, so we have our national land cover imperviousness data. And because the calculation of the landscape metrics are very sensitive to how we define our urban area. So it's very sensitive to how we reclassify the national land cover imperviousness data. So to fully utilize all the information in this data set, so we actually implemented 4 different reclassification schemes based on the NLCD imperviousness data. So as you can see, so the first scheme is to reclassify is to just like have different categories from 0% to 20% of imperviousness, then 20 to 50, 50 to 80, and 80 to 100. And the remaining, so we just use a breakpoint to just manually determine. So below a threshold of the imperviousness, it's going to be non-urban, and above that threshold is going to be urban. And so we have, for 4 of the different reclassification schemes, so we derive the corresponding landscape metrics and 2 scales. So one is at the census tract level on the left, and another is the block group level on the right. So the census tract level is our population source zone. So our goal is to downscale the population from the census tract to the block group. So based on the landscape metrics calculated at the census tract level, so we're gonna train a random forest regression model for each of our landscape metrics for the prediction of the population. And once the models were trained, so we're gonna transfer the model and apply the model to the block group level, because we have also calculated the landscape metrics and the block group level. And this predicted population and the block group level would serve as the population redistribution weight to downscale the population from the census tract level to the block group level. And this step is what we call intelligent. And then, because we are like targeting for like the more recent years, such as 2000, 2010, and 2020, so we do have like a finer resolution population data and the block group level for the validation process. So we're gonna do the accuracy assessment after the final downscaling. And so besides the landscape metrics, we also included like 2 baseline models for comparison. So the first baseline model 1 is the Dasymetric mapping of population based totally based on the imperviousness. So we simply just redistribute population from the census tract to the block group in proportion to the aggregated imperviousness value for each of the block group. So that is Dasymetric mapping based on the imperviousness. And the baseline model 2 is intelligent Dasymetric mapping based on the imperviousness. So the imperviousness value is gonna go first into the random forest regression model and then produce the predicted population at the block group level. And the predicted value is gonna serve as the population redistribution weight to further downscale the population. And so this table shows the accuracy assessment results for the state of Connecticut. So we have tested for 3 different years, year of 2000, 2010, and 2020. And we have mainly chosen 3 metrics for the accuracy assessment. So including the R squared, the percentage of people placed incorrectly, as we abbreviated as PPPI, and the MAPI, the MAP, is the median absolute error percentage. And here in this table, we are mainly focusing on the PPPI, the percentage of people placed incorrectly. And all the 3 metrics, they produce similar rankings among each models. And as we can see, the first 2 rows is our 2 baseline models based on imperviousness value, and the remaining one, each one corresponds to one of the landscape metrics. And for most of the landscape metrics, they also have 2 corresponding random forest regression model. So one is solely based on that landscape metrics. For example, for the ED, so which is edge density. So the first ED is simply using edge density in the regression model for the prediction. And the second is ED plus area, so which means besides the edge density, we also incorporated the area of each zones in the random forest regression model, because we found, so for some of the landscape metrics, so their calculation, its calculation has already considered, included the area information. But for some of the landscape metrics, so its calculation is totally independent of area. While area is also a very important indicator for the final population count. So we believe that the addition of the area information to the random forest regression model would make some improvement for certain landscape metrics while doing the downscaling. And the final two rows is is to use all the landscape metrics from this table in the random forest regression model, and the final row is all the landscape metrics excluding the class area, because the CA, the class area, directly correlates to the area information of each imperviousness category. So it directly corresponds to the area. So we want to see what's the accuracy if we exclude the class area and solely based on other landscape metrics for the downscaling. And by observing this table, and also I have compared each of the landscape metric based model with our two baseline models, compared to the best performing baseline model among the two. And I have color-coded each of the model so that the green represents the model is better than the best performing baseline model, while the red represents the model that is inferior to the best performing of the two baseline models. And the darker green, so the better the model, the darker the red, the worse the model. And we found that the best model among all the random forest models are actually we are using all the landscape metrics. So that makes sense because every landscape metrics are involved in the random forest regression model, so providing more and additional information. And for the single landscape metrics based model, so the model only implement one specific landscape metric, we found there's no universal best landscape metric model, but we found that the class area and the landscape shape index, they continually work the best. So these two are among the best of the landscape metrics for the population downscaling. And we also found that, as I have mentioned before, the inclusion of the total area information only improves the accuracy for certain landscape metrics, such as the edge density, the cohesion index. So these landscape metrics, during their calculation process, the area information is not included. So that's the reason why we've seen an improvement of the model accuracy after including the area information. But for other landscape metrics, because it already contains the area information, so the inclusion of the total area information does not have any significant improvement. And we also found, if you observe this table from the left for the year of 2000 to the right for the year of 2020, so we found actually, so the accuracies for those models are actually improved over time. So one speculation is that, all those landscape metrics are based on the National Land Cover Database imperviousness data. So the more recent data, we have a better quality. So that's the main reason why we are observing the accuracy improvement over time. And this table also it shows the accuracy assessment for the three states, Connecticut, South Carolina, and New Mexico. And we compared our landscape-based models with other traditionally used ancillary data set for the Dasymetric mapping of population. So in the upper portion, so we have so the fundamental method is area weighting, so which is simply redistribute population based on the area information of the target zone. And we also have other ancillary data sets such as land cover, total imperviousness, and some cleaned version of the imperviousness, the total road network, and the cleaned version of the road network, as well as night light imagery. And so if we simply observe the upper portion of this table, and I have highlighted the best performing model, the best performing other models for the three states, and we can see, so for the state of Connecticut, the best performing other methods is using the minor road density and the ancillary data set. But for the South Carolina, it's actually using the imperviousness less than 75%. And for New Mexico, it's a different best performing model. So we find that actually the best performing model is not consistent across study regions. So there's no universal best performing other method. So it totally depends on the study area. And in the middle, we have still have our two baseline models based on the imperviousness value. And in the lower portion, so we have the ORZ landscape metrics based model. And the color is still represented by the green. We compare all the models with the best performing other models. So compare each of the model with the highlighted yellow accuracy. And the green means it's superior than the best performing other model, and yellow means it's inferior to the best performing other model. And so our research result found that actually, so for the other ancillary datasets methods, so they actually show a general decreasing trend of the accuracy. So if we're moving from the high population density region to low population density region. So remember, so the left is the Connecticut and the right is the New Mexico. So left Connecticut has the highest population density, and the New Mexico has the lowest density, and South Carolina is in the middle. And if we observe the upper portion of the table, so we can see that for those other ancillary data sets, so their accuracy are actually having a decreasing trend if we're moving from high population density region to low population density region. But actually, we do not find that obvious decreasing trend of accuracy for the models based on the landscape metrics. So which means our landscape metrics based model are actually kind of robust to the changes of the population density of our studied region, which is a good thing. And as you can see, so actually the accuracies across different states representing different population densities. So the landscape metrics based accuracies, they actually do not change that much, but we still observe that, so there are more green models, more better models in the New Mexico, but more red models, more inferior models in Connecticut. So that is because, so for the New Mexico, the best performing other ancillary model highlighted in the yellow color, so its accuracy is much lower, but our landscape metrics, its performance stays already kind of stable. So that's the reason why we are observing more models performing better in New Mexico. And we also found that, so the class area, the landscape shape index, and the number of patches consistently outperform the best performing other models in all the three states. And the next figure shows the error percentage maps for the 4 states and the block group level. So basically, we can, based on these maps, we can observe some like spatial patterns of the error. And by observing the 4 maps and compare with some other ancillary data set, we found that actually, so the red represents the overestimation of population, and the blue represents underestimation of population. So the dark red represents like heavily overestimation of population, which is severely overestimation. So we found that those overestimation of population are normally corresponds to some like the CBD area. So those areas, they have like high population density. They do not have high population density, but they have high imperviousness value. So they are considered like the urban, but it's non-residential urban. So that is the reason why we have observed some overestimation. But compared with other ancillary methods, so this our landscape metrics model has already alleviated this kind of overestimation, because we believe that the overestimation of population could be alleviated by discerning the urban patterning, so that we could discern the residential urban from the non-residential urban. And this shows, this plot shows the median absolute value of the percentage error. So the x-axis, we have like the low imperviousness groups from 0 to 20%. In the middle is like medium imperviousness urban is from 20 to 60%, and the third group is the high imperviousness group from 60 to 100%. And the blue bar represents the landscape metrics-based model, while the red bar represents the imperviousness-based model. And we can see that across all the three groups, low, medium, and high imperviousness categories, our landscape-based model outperforms the imperviousness model. And so the reduction of the error is especially obvious in the high imperviousness category. And this table shows the bar plot for the percentage of the block group count over the total number of block groups by the different categories of error percentage between the estimated and the actual population. So in this table, so what's in the middle is like around like 0% of difference, which means like the prediction result is perfect. So it has a small difference from the actual population. But on the two sides, so the left side means severe underestimation of population, while on the right side, it means severe overestimation of the population. And we can see that our landscape metrics model, so the best landscape metrics model has a much more number of block groups lying in the middle, so which is a good region. And so the numbers is severely reduced in the two tails. And so this figure shows the two block groups in Connecticut. So one block group is a residential high imperviousness block group. Another is a CBD-based high imperviousness block group. So these two block groups, they have like almost the same imperviousness, total imperviousness value, and they have almost like the same area. So in like the traditional imperviousness-based model, so because the population is downscaled based on the total imperviousness value, so the downscale population for the CBD gonna be the same for the residential area, so which causes lots of overestimation of population in the CBD area, where it should not receive that population. But for our landscape metrics, so as you can see, so these two plots on the lower panel, so one shows the landscape shape index on the left, one shows the number of patches on the right. And we can see the two target block groups of residential block group and the CBD block groups. They show distinct different landscape metric values, so which could potentially help us to differentiate the residential urban from the non-residential urban and improve our accuracy and alleviate the overestimation of population. And for the conclusion and discussion, so we found that the best performing model is the intelligent Dasymetric mapping model using all the landscape metrics. And the best single landscape metric model is to use the class area and the landscape shape index. And compared with the other methods, landscape metrics are less susceptible to the decline in performance when moving from high population density to low population density region. It's not like other ancillary datasets method. And the improved performance of the landscape metric-based models can be attributed to the ability to capture pixel-level information, pixel-level impervious patterns. And the overestimation problem is alleviated by incorporating landscape metrics, but not fully resolved because we still found some overestimation in some areas. And the future research should use the landscape metrics derived from higher resolution imperviousness data. So our current landscape metrics are derived from an LCD imperviousness data of 30-meter resolution. If we are using a finer resolution imperviousness data and produce a more accurate landscape metrics, I believe it could like even further improve our population downscaling result. And so this work has been accepted on the computers environment and urban systems. And here are some other reference papers. Thank you so much.
and congratulations on having your paper accepted.
Thank you.
That's great news.
Yeah, I'm willing to take any questions.
I could be wrong, but I think your source for the land cover, I believe they're actually improving the resolution of that. We were going to move the LiDAR to land cover classification, but I think we're going to stick with it because they're going from what you said, the 30-meter resolution. I believe they're going to have a 5-meter resolution for the latest release.
Oh, you're talking about the National Land Cover Database resolution?
Yes.
Yeah, so as far as I know, so they provide like 30-meter for the land cover data as well as the imperviousness data. But I'm not sure whether they are going to release the 5-meter resolution because I didn't know that.
Yeah, it's kind of what we're working with. I could be wrong, but I want to say it's either that or NDVI, which I believe they generally have from the ones that are 5-meter resolution.
Okay, I will double check on that. Thank you. Yeah, I also used to generate the NDVI from like because like lots of the NLCDs they use the Landsat and the source, right? So it's like just like the 30-meter resolution is, I think, is inherited from like the satellite image resolution. Yep. Thanks.
All right,
Okay.
thank you.
Thank you.
Yeah.